Okay, so in this example, we have a delivery drone is descending vertically. When it is 20 meters above the ground, its downward velocity is 10 meters per second. To land softly, its motors provide an upward thrust that causes a deceleration of AS equal to 2S minus 4 meters per second squared, where S is the height above the ground in meters. And we ask, will the drone successfully land with zero velocity or will it crash? We also ask, at what height will its velocity become zero? So the first thing we're going to do here is we're just going to highlight the information that we have. We have that the delivery drone is descending vertically, so that's going to be important. And when it's 20 meters above the ground, its downward velocity is 10 meters per second. Then we have to land softly, its motors provide an upward thrust, which causes a deceleration of AS equal to 2S minus 4 meters per second squared. So we have that equation. And S is the height above the ground in meters. And then we're required to find, we have, will the drone successfully land with a zero velocity or will it crash? And at what height will its velocity become zero? So the first thing we're going to do is we're just going to write down everything we know underneath our problem. So we're going to have given. So what do we have given to us in this word problem? So we have that it's descending vertically. So it's going downwards, right? And when it's 20 meters above the ground, its downwards velocity is equal to 10 meters per second. And then we have to land softly, its motors provide an upward thrust. So its motors are giving an acceleration in the up direction of AS is equal to 2S minus 4 meters per second squared. And here this S is the height above the ground. Okay, so we're not going to ask the required to prove yet. We're just going to discuss the information that's given to us. So we have up and down. So we do have direction coming into play. So it is just like a y-axis. And to begin with, the delivery drone is descending downwards. So it's going in that direction. And then as it starts to land, its acceleration goes upwards. So let's choose the down direction as positive y. So down is going to be positive y. And that means up is going to be negative y. Okay, so that's how we're going to choose our coordinates in this case. You can obviously do it the other way around and make sure everything is adjusted accordingly. And if that's the case, so if down is positive y and up is minus y, and the reason why we're doing this is because we want to discuss the ground and the height to the ground. So, and we're starting at 20 meters above it. Let's use that to our advantage. Okay, so we're going to have down is positive y, up is minus y, which means our velocity at 20 meters is positive 10 meters per second. And remember, it's at 20 meters. And then our acceleration, which is a function of position, it is going in the opposite direction of motion. So it is going to be minus 2s minus 4 with our coordinate system that we're handling, where s is the above ground distance, which means we can also rewrite that velocity as v20 is equal to 10 meters per second. And then we're going to have this velocity as a function of distance. And at S0, we have the 10 meters per second. So again, all we've done here is we've taken the information that from our word problem and we set up a coordinate system to work to our advantage. Here we chose downwards as positive y and upwards as minus because it was in the air and it's going down. And because the acceleration is going in the opposite direction of motion, the signs need to be different, or one needs to be positive, one needs to be negative. And the way we chose our system, our acceleration will be negative. And it kind of matches the wording because we spoke about deceleration happening there. Okay, so now we can go a little bit further from this. So let's just still keep the yellow part so we can see what it looks like. We're requiring to find, so let's add in this information as well. We are going to look at what are we required to find. And we are looking, are we going to land and not crash? Or are we going to crash? Now, if we look at that, what that basically means is when we get to the ground, remember S is the distance from the ground. So when S is equal to 0, is the velocity 0? Because if the velocity still actually had a value to it, you're kind of going into the ground at a speed. And that means you're going to crash. Okay. And then the second thing that we were required to look at is at what height, so at what S value, because remember S is the distance to the ground, so that is height, is the velocity equal to 0 meters per second. So we have two things that are kind of connected, but we're looking at, are we going to crash? And at what height will the velocity be equal to 0? Now we're going to go back to the information we have. We had a function there. We're going to start with that function because when we're looking at this, we want to know the velocity. So when is the velocity equal to 0? So the velocity is a function of position. And I'm just going to do a quick little diverge thing to remind you of the process that we follow. We have a definition of velocity is dr dt. So velocity is dr dt, or if it's in one dimension, it's ds dt. And our definition for acceleration is dv dt. So if we have position, we take its derivative and we get velocity. If we have velocity, we take its derivative and we can get acceleration. But now, if we have acceleration, to get velocity, we can take the antiderivative, so we can integrate. And if we have velocity, we can integrate to get the position. So that's the fundamental information that we are going to use here, because we want to find a function for velocity. Specifically, we want a function of velocity with respect to position. So that's what we want to actually find so that we can answer these two questions, question 1 and question 2. And to do that, what do we have given to us? We have a S is equal to minus 2s minus 4. And remember, I just made it minus because of my coordinate system, and I chose down as positive and up as minus. So we have the acceleration function. So if we have the acceleration function, we take its integral to get the velocity function. So to do this, we actually start with the definition of acceleration. So we're going to have acceleration. So our definition of acceleration is equal to dv dt. But let's also put in the fact that the acceleration that we have is a function of position. So we have dv dt, and that gives us s, v, and t variables to work with. Now, if you can't really see what's happening, let's actually sub in that acceleration function. So it's minus 2s minus 4 is equal to dv dt. Now, traditionally at this point, you're like, if you want to do the integration, you would have just said, okay, a dt is equal to dv, and then you would have integrated both sides. But that only works if it is separable and that everything on this side is a function of time or constant. So it involves the variable t or its constant. And then everything else involving v is on the other side, v or constant. But right now we have a is a function of s. And s is not really compatible with this dt yet because s is actually a function of time. So we can't just treat it like a constant here because it is a function of time. So we have to use our other tricks that we have from maths. So I'm just going to rub that out a bit so we don't need that anymore. Now, tricks we need from math is that our definition of velocity. Velocity is a function of position, but position is a function of time. And we look at the rate of change of a function within a function. We are looking at, in this case, the rate of change of the outer function with respect to its inner function, so that's ds, and then the inner function with respect to its input. So let's just go through that a bit slower. So we have an inner function, and then we have a outer function, which is the velocity. So the velocity changes with respect to the position. Changes with respect to position, and position changes with respect to its input of time. Respect to time. So if we're looking overall, we're looking at the entire velocity, we have to look at how the position changes with respect to time, and then how that change affects the velocity. And that's where that chain rule comes in with that multiplicative or multiplication situation. So what we're going to do is we're going to replace this dv dt with this version from the chain rule. So we're going to have dv ds and ds dt. And we're just going to bring down that minus 2s minus 4. Now we have to look at what do we have and try and clean it up a bit. So we also know the definition of velocity. So the definition of velocity is ds dt. So we can replace this with v. So we go ahead and replace that with v, and we can move them around, swap their places because they are commutative. So we have v dv ds minus 2s minus 4. And what we're going to do is we're going to take the ds across by multiplying it by ds on both sides, basically. So we're going to get v dv. And now we're going to check, is it separable? Remember, if it's separable, everything to do with s will be on the one side, and everything to do with v will be on the other side. And if it is separable, we can now integrate. Now, again, we're going to quickly just do a quick divergence here. When we do our integration, we can do it in two ways. We can do the indefinite, so we can do it as is. It would help if my pen actually wrote. Let's just try that again. And then we will have to, we will get integration constants. And then we'll have to solve for the integration constants using our initial conditions. The other method or approach is we can actually give the integrals limits. So integration limits. So we're going to use definite integrals there. And I'm going to choose this one when I'm doing my working out. So here I put the integration limits directly in. So I'm going to be like, okay, well, what is S0? Because when you look at your integration limits, you're going to have S0 and some S, which we're going to solve for. And we're going to have V0 and some V we're going to solve for that is connected to that S. So what is our S0? So let's go back to the information that we have. So let's just scroll back up quick. So the information that we have is that we have V is positive 10 meters per second when S is 20. So we have S0 as 20, a V0 as positive 10. So we can put that into our limits. So let's just go back down now, and we're going to plug it in. So we have S 20, and when S is 20, we have V is positive 10. And then we have the ones we want to actually solve for. So we're going to have S, we're going to have V. Now we do need to clarify here that this S over here is not the same one here yet. We're going to have to distinguish them, and we're going to distinguish them by just making the ones in our integration as like dummy variables. So we're just going to add apostrophes to them just to clarify the difference between S and DS. And I'll show you again why that's important when we get to the next few steps. And we're going to do the same for the DV side. Okay, so now we can actually start doing our integration, and I'm going to do it the long way. So when you have 20s minus 2s prime plus 4 brackets ds prime, I can separate this out. So I can take this and this on this side. So I'm going to have 20s minus 2s prime ds prime plus 20s 4ds prime. I can also take out the constants, so this actually becomes minus 2 20s s prime ds prime. Now bear in mind, I'm doing this the long way. I'm just trying to cover as many possible questions as possible from someone who's watching the video. And we're going to have 4, so you can skip some of these steps. S prime, if you're comfortable with integration. Then the other side, this is going to just stay the same for now. Don't forget the other side. V prime, dv prime. V prime, dv prime. Okay, now we can go ahead and actually do our integrations. So minus 2, we're going to have s prime squared divided by 2 from 20 to s plus 4 s prime 20 to s is equal to, we're going to have v prime squared divided by 2, 10 to v. Okay, now we can actually go ahead and sub things in. So we're going to have this s prime now. It gets subbed in with that s, which is at any s point. S squared divided by 2 minus 20 squared divided by 2 plus 4s minus 20 is equal to v squared divided by 2 minus 10 squared divided by 2. Now we just need to neaten it up, so the 2's will cancel. That's kind of great. And we can also try and get rid of the 2's as denominators here by multiplying everything by 2. So we're going to get 2 times by minus 1. So that's just going to give us that minus 2 s squared minus 20 squared plus 4 times by 2 is going to give us 8. S minus 20 is equal to v squared minus 10 squared. Okay, now we can neaten it up a bit. So continue just multiplying everything out. Minus 2s squared plus 2 times 20 squared plus 8s minus 8 times 20 is equal to v squared minus 10 squared. And we want v as the subject of the formula because remember the whole goal of this was to find an equation for v where v is a subject of s. So we want v by itself. So we want v squared minus 2s squared. I'm putting all the things connected to s first. So we're going to have that 8s. Then we're going to have 20 times 20 gives me 400. And then, so 20 times 20, 400 times by 2 gives me 800. Don't know why that took me so long. And then 20 times by 8 is 160. And then plus 100. So we're going to have 800 minus 60 gives us 740. So v squared is equal to minus 2s squared plus 8x plus 740. Now we can actually start answering our questions. And in case you're wondering why, it's because this is v is still a power of s, and it is squared minus 2s squared plus 8s plus 740. And when we're looking at what to prove, we're kind of looking at when is the velocity vs equal to 0. So we don't have to make the subject of the formula just vs. 0 squared is still 0. So we're going to keep the math easy for ourselves. So we're going to have 0 is equal to minus 2s squared plus 8s plus 740. And that is going to give us s squared plus 4s. I'm dividing everything by minus 2. Minus 370 is equal to 0. And this is just a standard quadratic equation that we can solve. So let's just give more space. So we have s is equal to, and remember when you're doing your quadratic equations, it's minus b plus minus b squared minus 4ac divided by 2a. So that is your a, that's your b, and that's your c. So we're going to get 4 plus or minus the square root of minus 4 squared. If I was multiplying through by minus 2, let's go back here quick. Over here, I multiplied by minus 2, so this should be minus 4. Okay, minus 4 squared, minus 4, 1 minus 370 by 2, 1, and that's going to give us 4 plus or minus 38.68 divided by 2. So S is going to be approximately equal to 21.34 meters, and S is approximately equal to minus 17.34 meters. Now this is saying that the velocity is equal to 0 when S is either of these two. So 21.34 meters is 21.34 meters. So let's clarify what this is saying. Let's go back to our system here. The ground is y is equal to 0, right? Now 21.34 is sitting somewhere up here-ish, 0.34. And then we're going to have somewhere down here is the minus 17.34. So looking at that and just investigating the case where the velocity is equal to 0, it is going to crash into the land. But if we are not comfortable with that, we can find out exactly what is the velocity when it hits the ground by looking at solving the velocity where s is equal to 0. So we go back to this equation that's over here, and we look at what does it look like when s is equal to 0, when it's on the ground. So that's what I meant by that second one was connected to the first one. You could solve it by just investigating there, but we can actually just go ahead and say v at 0 squared is equal to minus 2 0 squared plus 8 times 0 plus 740, which is going to give us v squared is equal to 740. So v0 is approximately equal to the square root of 740, which is, that's not approximately yet, which is approximately equal to 27.2 meters per second, plus or minus. So in this situation, again, it has a velocity, so it's going to hit the ground at 27.2 meters per second square, or meters per second. And that means it's going to crash.